My name is Daehyeok Kim. I'm a PhD student at Carnegie Mellon. Today, I'll tell you how we can virtualize RDMA networking for containerized clouds with FreeFlow. So there are two recent trends in developing cloud applications, containerization and RDMA networking. Container solutions such as Docker and LXC offers lightweight isolation and portability, which lowers the complexity of managing and deploying the applications. On the other hand, remote direct memory access, or RDMA networking, offers higher throughput, lower latency, while maintaining lower CPU utilization. As a result, many applications, especially data-intensive applications such as Spark and TensorFlow, adopt container or RDMA networking, but not at the same time. So you may be wondering why they cannot be used together. So I'll explain why in the next couple of slides. So what's the key benefits of containerization for applications, especially network applications? With containerization, for traditional TCP networking, containers can use their own network namespace, which means they can use their own IP addresses regardless of the address of the host namespace. So it supports namespace isolation. Moreover, even when the container is migrated to another host machine, it can retain its IP address, which supports the portability of application running inside the container. However, when it comes to the RDMA networking, containers cannot support two properties because they are in conflict. In this case, containers have to use host namespace to directly interact with RDMA networking interface card. Because of this, each container cannot have isolated network namespace, which means all containers have to use the same IP address as the host namespace. And another issue happens when migrating containers. Since the namespace on a new host machine uses another IP address, the migrated container also has to change its IP address to a new IP address, which limits the portability of the container. So one natural solution we can think of would be using existing virtualizing hardware-based virtual I/O virtualization solutions such as SRIV. At high level, SRIV-capable NIC provides a set of virtual network interface called virtual function, and we can set different IP addresses to each virtual function. Then the virtual machine or container can use virtual function in a host namespace, but with different IP addresses. This provides you with namespace isolation in some sense, with one caveat, which is that you're limited to a set of IP addresses that are assigned to a particular virtual function. So while this might not affect your network namespace isolation on a single machine, when you have to deal with portability, this limits that ability. So as a result, containerized applications today cannot use RDMA networking, and it results in suboptimal performance. To demonstrate this, we ran different neural net training workload on TensorFlow with container and with TCP networking and also native RDMA networking. So you can see here the containerized TensorFlow with TCP networking shows significantly worse performance than the native RDMA case. Here, native RDMA networking can improve the performance by around like 10 times. So our goal was simple. So we wanted to make containerized application to be able to use RDMA networking while achieving isolation and portability. In this talk, I present FreeFlow, a software-based virtual RDMA networking solution for containerized application to achieve this goal. With FreeFlow, any existing containerized RDMA applications can run with minimal or no code modification. And our evaluation with data-intensive applications, including TensorFlow and Spark, show that FreeFlow can achieve very high performance, which is close to native RDMA performance. Now, let me explain the key ideas in designing of FreeFlow. In a native RDMA case, an RDMA application directly talks to RDMA NIC via Verbs library, which translate the user space Verbs user space RDMA commands into NIC command. In FreeFlow, we introduced a software layer that virtualizes RDMA networking for containers. At high level, the FreeFlow layer gets Verbs call from the app and process them by interacting with RDMA NIC on behalf of the app. Since FreeFlow allows the container run their own network namespace, it supports isolation and portability. However, while realizing this idea, we faced several challenges, and to explain them, I first briefly introduced the background on how native RDMA works. So let me bring a simple example where host 1 wants to write write the contents in memory 1 into memory 2 on host 2. An RDMA app and RDMA NIC communicate through two different communication paths called control and data path. In the control path, the RDMA app issues a set of verbs command to set up RDMA context and register memory region. And once the context gets ready, it exchanges the context with the remote side to establish RDMA data path. Then it can post work requests, for example, write requests in this case. Then in the data path, the NIC processes work request by directly accessing memory without involving CPU, where the most of the performance gain from RDMA comes from. Now let's bring FreeFlow into the scene. FreeFlow provides an app inside the container with virtual resources for both control and data path. When an app creates a context, FreeFlow layer creates a shadow memory for app's memory region. Later, in the data path, the NIC will directly access this shadow memory instead of app's memory region. Because of this, these two memory regions must be synchronized. Then it creates a corresponding shadow context and register it to RDMA NIC. Then the NIC will directly access the shadow memory in data path. Well, it sounds like a simple idea. There are two key challenges to achieving this. The first one is how to force verbs call from the app and FreeFlow layer efficiently. And the second challenge is how to synchronize the shadow and application memory region without incurring much system resource overhead. I'll explain how we solve these challenges in next slides. The first challenge is how to efficiently intercept and forward verbs call from the application. That is, what the app should send the FreeFlow layer to forward the verbs call correctly and efficiently. So we first came up with this design where we put the shim layer under the app and intercept the verbs call from the app. In this example, the shim layer intercepts post send, which is used for posting a send or write work request. Then the next question is what the shim layer should forward to the FreeFlow layer. Our first attempt was to forward the function call and argument as it is. But it turns out it failed. Why? Because as you can see here, the verbs call takes some pointer argument, which points to another data structure. So without careful serialization, these attempts can be incorrect. And the second approach we took was serialize the arguments and then forward them. But we observed that the QP data structure in this case indeed contains lots of pointer member variables, so which makes the serialization very difficult or inefficient. So how did we solve this problem? Fortunately, we found a hint by looking at one step deeper inside the existing Verbs library. When the app issues a Verbs call, the Verbs library outputs a serialized parameter to send the corresponding NIC command to the physical NIC. So this means that the complexity of Verbs call arguments can be simplified internally by the Verbs library. So based on this observation, we decoupled the FreeFlow layer into two parts called FreeFlow router and FreeFlow library, and make the virtual NIC, or VNIC, as an interface between them. And our shim layer intercepts the serialized output of full-fledged Verbs library instead of intercepting the app-facing API call. Then we make it to forward the call, Verbs call, to virtual NIC on the FreeFlow router. This way, Verbs call can be forwarded correctly to the FreeFlow router without explicit serialization. And the second challenge is that how to synchronize the shadow memory and app memory region without involving much system overhead in the data path. As mentioned earlier, the shadow memory is the copy of application memory region, and the NIC directly access the shadow memory instead of the app memory region. And those memory regions must be synchronized for correct data path operations. However, we observed that the synchronization is not trivial because of their characteristics of RDMA operations. And I'll explain this challenge with an example. Let's assume the container 1 wants to write the contents in its own memory region, mem1, into another memory region, mem2, on container 2. So when the write request has been issued, the FreeFlow router needs to somehow copy the data from the mem1 to its shadow memory region. And then the NIC read the data from the shadow memory and then transmit it to the NIC on the other side. Then the receiver NIC put the data to the shadow memory 2 without CPU involvement. Then the problem happens here. Since there is no signal to the FreeFlow router does not know when it should forward or copy the data from its shadow memory to application memory region. So one straightforward solution for this would be explicitly synchronizing two memory regions. But this could be either inefficient or ineffective. So if it is too frequent, it would consume excessive amount of CPU cycles and memory bandwidth. So it's not is undesirable result. And if the frequency is too low, the app can end up reading wrong data. So both results are undesirable, right? So how did we solve this problem? We observe an opportunity from the fact that the containers are just the processes in the same machine, and they can share the memory regions. Since both FreeFlow router and applications are running inside the two different containers on the same machine, they can share the memory region. Now, we know that the application region, memory region, and shadow memory can be allocated on the same physical memory region. Then the question is, how can application allocate its data buffer memory region to shadow memory regions? FreeFlow provides two methods for this. The first method is to allocate the app's memory region using FreeFlow's memory allocation API, which allocates the data buffer, application's data buffer, to shadow memory region. But it requires some code modification. And the second method is remap app's memory region to shadow memory region. So in this method, while it does not require code modification, it requires the app's memory region to be page aligned. And from our experience, the most of RDMA applications are already make their data buffer page aligned. So the FreeFlow router can just remap the application's region to the shadow memory region. Because each method has different trade-off, we provide both methods for the developers. So the end result is the system, FreeFlow, that allows you to combine two great technologies, containerization and RDMA networking. In particular, we introduced FreeFlow router and FreeFlow library with two key ideas. First, we leverage the internal structure of Verbs library to forward the Verbs call efficiently. Second, we designed a zero-copy synchronization method in data path and provide two different methods for developers. As a result, FreeFlow can achieve near native RDMA performance for containers while supporting isolation and portability, as you'll see next slides. So we implemented FreeFlow by modifying the user space Verbs library and drivers, and we implemented FreeFlow router in C++. And our testbed consists of two servers equipped with RDMA-capable NICs, and we use Docker as a container solution. So one nice thing about RDMA is that it provides a latency of single-digit microseconds, which is incredibly valuable for latency-sensitive applications. So we first measure the latency of RDMA operation on FreeFlow and native RDMA case. So two containers were running on two different host machines. And this graph shows that the RDMA write latency. So here, x-axis is the message size, and y-axis is the latency in microsecond. And we can see that compared to the native RDMA case, FreeFlow has at most 0.4 microseconds of extra latency. And this extra latency is mainly due to the communication delay between the FreeFlow router and FreeFlow library for control path. And high throughput is another important advantage of using RDMA networking. And this graph shows the RDMA send throughput. And the sender sends 1 gigabyte of data with different size of messages. And here, x-axis is the message size, and y-axis is the throughput in gigabit per second. And we can see that the message size equal or larger than 8 kilobyte. FreeFlow gets full throughput as native RDMA. But when the message size are smaller like 2 kilobyte, the FreeFlow chip nearly half of the full throughput. So this is because the throughput is bounded by the capacity of control path between the FreeFlow router and FreeFlow library. What about the real-world application performance? So to measure this, we trained speech recognition recurrent neural net model on TensorFlow. And we compare the performance of container TCP networking and native RDMA and FreeFlow. This figure shows a CDF of time spent for each training step. So we can see that the median training time with FreeFlow is around 8.7 times faster than container TCP networking, and it is also very close to native RDMA case. So to conclude this talk, containerization today cannot benefit from the high performance of RDMA networking. And existing virtualization solutions such as SRIB don't work for this case. So today, I introduce FreeFlow that enables containerized application to be able to use RDMA networking while supporting isolation and portability. We addressed two key challenges in both data path and control path, and show it can support close to native RDMA networking performance. Please check out paper and our GitHub repo for more details. And with that, I'm happy to take any questions. Thank you.
This is Wonso from Sonos. Very nice piece of work and talk. Thank you very much. I got two questions. One is simple one, and then maybe two of them are maybe very simple. One is, do you have any local copy optimization, such case that you move one memory from the other memory which exists in the same machine?
So what you're saying is if the two containers located in the same machine,
Yes.
yeah, so then the data goes through the shared memory path instead of going through the RDMA NIC path.
Okay, good. Second question is, do you have any way to prevent the container migration during the active RDMA transaction?
Can you say that again?
Do you have any way to prevent container migration during the active RDMA transaction? Can you deal with that?
So actually, in the current prototype, we didn't consider that case, but it's a good future direction, I guess.
Okay, hope that is resolved.
Okay, thank you.
Any more questions?
Yeah, good question. Is this technique available? So NIC virtualization, can it help virtual machines? Can you do virtual RDMA for virtual machines with SRIOV? So what I'm trying to get to is like, what
Please
is
speak louder, please.
What is the container-specific piece here? When you say existing solutions for NIC virtualizations don't work, so do they work for virtual machines? The NIC virtualization?
I see. So what you're saying is does SRIOV work for virtualizing RDMA for virtual machine case?
Yes.
So it works in some sense, but it's also very limited. So there's some work about virtualizing RDMA for virtual machine using SRIOV, but it does not fully support some isolation and portability as well.
So this exact same solution would also help virtual machines, right?
So what you're saying is, does FreeFlow can apply for virtual machine case?
Right.
So we can leverage some like a memory mapping kind of technique we are using in this case for virtual machine case, but I'm not sure whether we can exactly, we can apply the exactly same mechanism for a virtual machine.
You showed that container migration case, the IP address change happens. And how do you solve that problem with the FreeFlow?
So in FreeFlow, the containers are running on the virtual networking mode, which means the container can retain its IP address even if it's, it moves to another host machine.
Okay.
And the FreeFlow router maintains the mapping between the container's IP address and the host IP address.
Does the FreeFlow router knows about the new IP address that is coming here?
Yeah, so actually in this, I didn't mention in the talk. In the paper, we mentioned there's an orchestrator we leverage to manage the mapping between the container's IP address to where it actually physically located in.
So I'm wondering what is the CPU utilization of FreeFlow? So if you have so many containers and you have the address translation happening here, so what is the CPU utilization?
Yeah, so that's good question. So, so the CPU, so the FreeFlow router takes a single, in our prototype, FreeFlow router takes a single CPU core to process all, to handle the all container in the same machine. But that limits our performance as shown in the, our evaluation, like this case. So if we dedicate more CPU core for a FreeFlow router, then it can support more, higher throughput.
But isn't that going to cause some trouble, such as when multiple cores are operating on the same area of memory? Is that going to cause trouble? Do you have that concern?
Can you
For
clarify?
example, if one core is operating on one memory and the other core is working on the same memory area, are you going to do you have some concerns?
Yeah,
on
then
that part?
we need to do some locking between. For that memory region, and it can affect the performance.
I see. Okay, thank you.
This is Yang
Quick
from Harvard.
question.
Yeah, just one question. Quick question. So, is there any security concern between the among the shared memory between the container app and the FreeFlow router?
Yeah. So FreeFlow router allocate the shared memory region for each container base and also each RDMA connection. So for example, the arbitrary container cannot access the arbitrarily shared memory region.
Okay. Thank you.
All right, let's thank Daehyeok one more time.